I think we're ready to start. Okay, so thank you very much for joining us. Ayal, you can take it away. We're very happy you're here.
Okay, thank you, Stefanos. I'm glad to be with you guys, even if remotely. Um, I prepared a couple of slides and to share with you some presentation. If you feel something is boring, let me know and I'll speak faster. If you want me to stop and elaborate more on something, well, I should leave enough time once I'm done. But I'm happy to do it interactively. If something's urgent and burning, then and you can't wait till I finish. That's also fine. So the topic I'd like to sort of share with you is sort of compiling for heterogeneous platforms. And since I visited your campus and Wenmei's team many years ago, we had heterogeneous platforms then and there, right? They were essentially CPUs and GPUs. So we know for a long time that one size does not fit all. It's no longer a homogeneous CPU that does everything. We need to improve efficiency, Moore's law and everything. But I think we're taking this one step further, and that's what I'd like to share with you. So it's no longer just a CPU and a GPU, or you can think of even a CPU is no longer homogeneous. There's big, little, and GPUs have tensor cores, so they're also not the single type of compute engine within a GPU and within a CPU. And the domain I'm involved in for several years is autonomous driving in a company called Mobileye. And I'll sort of speak from that perspective, but this is sort of my personal view on things. So any questions you can ask, I'd be happy to try to respond as much as I can. So before we dive in, there's a very nice slide I like to borrow from a decade-old presentation of halide. And it's essentially this triangle. I hope you can see it if it's large enough. It essentially says, yeah, can you see it?
Yeah.
So essentially, there's a trade-off, right? Why are we going for heterogeneous? Because essentially, we have different points in space that we want to optimize for. And what do we want to optimize for? Well, there is sort of a first message, and this goes back, if you want to trace back, I can send you the link, but this is the reference, like a decade-old presentation by halide folks. And the first message, which sort of struck me at that time, was there's an inherent trade-off in terms of performance between parallelism, locality, and redundant work. So if you want to go faster, it actually probably means we want to parallelize, right? If you want to optimize for parallelism, then you may lose locality. And why is that? Well, you want small elements of work to be totally independent, so they can run anywhere and at any time. And if you do that, then, well, I don't know where something ran before on what core, and so I lose locality. And for those of you who are familiar with CUDA and OpenCL, they sort of strive to increase parallelism. There's a bunch of threads going around, work groups or warps, or however you want to call them, or thread blocks, and the compute units can process any work group at any given time. And so to maximize parallelism, we're free to schedule any work group on any compute unit. And as a result, we sort of lose on locality. We have no idea what work group process ran on that compute unit before us. If we want to optimize on locality, we want to keep data and operate on it as soon as it's produced. So we actually want to stitch together elements of work. right? And that stitching sort of reduces the granularity of parallelism, right? Another point in the space is redundant work, right? Which means, well, if I have some dependence between sort of some thread computes something and another thread needs it or is dependent upon it, then in order to increase parallelism, I can actually let the second thread pre-compute it. And so do some redundant work. The work has already been done by the other thread, but in order to be independent of it, I can actually have both threads process the same work, thereby increasing the total amount of work, but freeing more parallelism. And you need to keep this trade-off in mind, and different points in space may be more efficient in different parts of your computation, and I'll try to get into that later in my talk. So in order to sort of tell you more about where Mobilize is at and the context of my work in the last 5-6 years, there is an online talk by about 2 hours, which is up on YouTube, given by the CEO and the CTO of Mobileye on October 1st. So it's like a month and a half old. And of those 2 hours, I want to sort of dive into 10 minutes of Professor Shai Shalev-Swartz of the Hebrew University, who is going to talk about the hardware aspect of Mobileye. And I will then respond with any questions you may have and complement that with our work. So let me dive into this 10-minute presentation, and I'll stop it when he moves on to the next topic. That was the 10 minutes going back to this AI day. You're most welcome to, I'll send you the link on the slide. You're most welcome to listen to the entire 2 hours. It's mostly about AI. This is the relevant part that talks about the architecture and the chip that's running in the car, and concluding with, okay, we built this chip, it's highly heterogeneous, 5 different architectures, and there are multiple instances of each of these accelerators. And now the problem is, okay, so how do we handle that level of heterogeneity? And you already have the answer, right? We need compilers. So any questions before I continue?
Yes, we have some questions. Well, one is, well, first of all, thanks a lot for the video. I think this actually sets the discussion very nicely on like why we need compilers. One question we have is, are you able to share any architectural details of this CGRA, such as how many functional units, how much routing between them, etc.?
Unfortunately, the answer is, as anticipated, I think, negative. But I will try to elaborate more on how we address them. But yes, in more general terms. But it is a CGRA, and there are many other CGRAs in the market. And that's about what I can say.
Okay. Yeah, sure. So I guess two questions I have is the MIPS CPU is basically a general purpose CPU that exposes MIPS assembly. That's very interesting. I mean, I don't know about you folks. I don't think I've seen recently like a CPU that you program with MIPS. This is what we used in my undergrad to learn assembly, but I haven't seen it in practice. This is so cool.
Yeah.
Nice.
IQ6, and I think prior instances of the IQ chip you need some CPU, right? You need to run Linux, and the MIPS is the CPU that we're using.
That's cool. Okay. Yeah. I mean, it would be, I don't know how relevant it will be in the rest of the talk. I would be interested in knowing how it feels to compile from MIPS, like for a compiler person, basically. Like how it compares to different architecture.
I think that's the more standard part of our chip and the software stack and how we compile for it.
Yeah, right. I agree. Compared to the rest.
And going forward, the next generation is already announced that is going to be using a RISC-V CPU. But it's a CPU, right? For all practical purposes, its goal in life is to run all the things that we actually do not offload onto other specialized accelerators. Right. So you have a CPU in every heterogeneous system that's devoted to making sure the accelerators are driven correctly and taking care of things that are not accelerated using the accelerators. So in that respect, it's a standard CPU, and essentially you can sort of choose which version of CPU you want to employ on the chip.
Mm-hmm. Yeah, makes sense. Okay, cool. Thanks. I think these are the questions we have up to now. So I guess we can continue with the presentation.
Oh, here. So here's an example demonstrating the use of different accelerators on a network. So this is a YOLO, you only need to look once network. The final part has a non-maximal suppression layer, which employs some irregular control flow. By irregular, I mean something that's not a deeply nested loop and actually has, data-dependent branches. And as such, the right accelerator to offload it over is the MPC, which is multi-threaded, but each thread can employ, branching. So each thread can go independently. On the other hand, if you have convolutions, they are best assigned to the XNN, which is essentially a convolution and matrix multiplication engine. And this is the bottom part, right? There's a lot that goes before. And there are layers that do box processing, which are regular, but it's not convolution, right? So they are best assigned to the PMA, the TGRA, and there are also occurrences of several permutation layers that are best assigned to the VMP. Right, to standard VLIW, you don't really need a CGRA to process them. So this is just one example of where heterogeneity can come into play in one program or in one network. So what is the software stack that Shai Shalev talked about, and how do we compile to this heterogeneous platform? And so the answer is all on this slide. On the left hand, you see sort of the input program or network in AI, using whatever AI framework, TensorFlow, PyTorch, that you'd like. And on the right hand side, you have the heterogeneous architecture. And in order to reach it and compile down to it, we actually use three different compilation tools. The first takes care of compression and transformations that actually do not maintain precision. So this tool is Python-based. It's closely connected to the frameworks we're sort of working with. And first and foremost, applies quantization. And do you know what quantization is about? Do I need to spend any explanation of.
By quantization, you mean reducing the accuracy of floating point operations?
Exactly. So when you train a network, you train it on floating point 32 bits, right? Which is sort of something you can derive and use derivatives and back propagate and the like. But when you want to run the trained network in the car, so we're doing inference, right? When we drive, we're after training, right? We've trained the networks, and now we actually want to apply inference. Then it's very important to actually reduce the data type sizes as much as possible to be most efficient, right? It saves you on computation. It saves you on memory. It's really important to do it. But this compression, right, reducing the size of each data element comes at a price, right? You lose or you change the accuracy. So this has to be done carefully. You're essentially changing the semantics, if you like, right? You take a floating point program and you compile it, and you produce results that are sort of not bit accurate, if you like. And this happens in many cases. So there are different quantization approaches. You can take the trained network and do something that is pretty fast, called post-training quantization. But you can also try to retrain with quantization in mind. So you apply training in order to come up with a more accurate or a result that retains better accuracy, but that requires more sort of compile time this stage. But essentially, this stage has to be sort of confirmed manually, because you're essentially changing what the result of the program is, right? Something compilers are traditionally not trusted with, right? Especially in the automotive domain, we want to make sure that we're doing things correctly, and I'll touch more about that. We are very pedantic, right? This is a matter of life, right, and death, right? So.
Sorry, just two questions here. So the first is just to be sure you're still using floating point. You're not going to fixed point, right?
We are going to fixed point. So we're reducing where it depends on what the data type you're reducing to. It could be a smaller floating point representation. It could be an integer.
I see. Okay. Interesting.
You want to reduce it as much as possible, right? And as much as the architectures support.
Mm-hmm. And I'm sorry, but it's not very clear to me. What do you mean by manual, I guess, verification? Like, how does that look like, roughly?
So whoever came up with this network, sort of, suppose you have a network that identifies traffic lights or road edges, or identifies, pedestrians and whatever you sort of encounter during driving. So you have the algorithm developed that produces the input program, and you're in some sense in this tool, using this tool, you're modifying their program. So they trained it until they sort of were okay with the results of the accuracy, and now you're sort of affecting their accuracy. So you need to go back to the original programmer and get the confirmation that, listen, this is the how we're going to run your program in the car. Are you okay with it? And we need to sort of get a confirmation that, yes, this is okay. Right? This you have not lost accuracy in an intolerable amount, but in some sense. Because we are sort of dealing with compilation, and whoever develops the algorithm is sort of in charge of making sure that this answers the problem of whatever identification is taking place here. Um, so so this first step changes semantics, could change semantics, could affect accuracy. It needs to be sort of certified, if you like.
Okay. Thanks. Good question. Oh, we have another question from the audience. Yeah, sure.
Yeah,
Yes.
so when you're verifying this, it's essentially testing, right? Or are you going with methods such as, I think there are like verified models and like et cetera, that are coming up. I don't think it like applies to like very large models. I think it's the moment scalable to like smaller models, but yeah, just wanted to ask that.
So it's a good question. I'm not sure I know the answer, but
Okay.
you know, it's sort of we're trying to provide a tool that provides this transformation, and it needs to be certified, verified, in whatever means whoever developed the program to begin with asserts that it's okay. Right.
Okay.
And you can think of, well, how did they train the original network, right? How did they provide the original network and concluded that it's okay? I don't know, right? That's the training development side of work. That's that I'm sort of not involved.
Got it. Okay, thank you.
So once we've reached that point, from here on down, right, this is standard compilation. So the next tool is an MLIR-based tool that takes the trained and quantized network and applies standard compiler transformation. So we need to figure out, okay, which parts are going where. So essentially do the graph partitioning transformation. Once we know which layers go to an accelerator, one optimization is sort of trying to fuse them together, which, if you go back to that triangle, is trying to improve locality, right? If you fuse two layers together, you have sort of a large layer that's sort of keeping data inside, optimizing for locality. Some of these accelerators also necessitate tiling for data, and I'll touch a little bit about that. But again, optimizing for locality, that also involves pipeline. So these are high-level transformations that we leverage MLIR in order to apply them.
Ayal, what
Yes.
is the host model used for things like fusion and tiling?
That's a very good question, and essentially, you sort of need to figure out a good cost model for each of these accelerators. And one way to achieve it is to actually continue on compiling and then get some metric about the merit from the resulting assembly and even from executing it.
So it's some form of auto-tuning?
You could think about it as some form of auto-tuning.
I see.
And in some cases could be easier to solve using heuristics. You know, it could be obvious what the right size is or what the appropriate good enough size is. And for others, you may actually need to auto-tune.
Okay. Just, I guess, a follow-up on this. I think it would be very interesting to hear your opinion on whether you found recent academic works useful in this practice. So there has been a lot of work the last couple of years on cost models coming from academia. Has that been useful for you?
I would say that is still, from my perspective, still work in progress to map those works to our context.
I see.
So I think it sounds very appealing. But I don't have anything I can sort of share at the moment. So this does deserve more attention, and hopefully, once we have established that, we can sort of say more about it. But it is a challenge, and we hope we can meet that challenge in a better automated way than we currently can talk about.
Sounds good. Yeah, thank you.
So once we have cut out the part of the program or the network that needs to be assigned to each accelerator, now we want to compile for each of them. And we actually have made a decision a couple of years ago in terms of how do we want to reason about this heterogeneous platform. As we talked earlier, we have a handful of different architectures. C is not a very good language or a programming model for something heterogeneous, right? There is one memory space and one sort of programming abstraction. We've used OpenCL as the underlying programming model to reason about the various accelerators. So our MLIR compiler actually generates OpenCL C code. We've augmented that with a tensor and tiling library, which we've open sourced. You can look it up. Because OpenCL, even though it's very appropriate for heterogeneous architectures, is still C-based. So if you're looking at tensors and tiling, there's still more to be desired, and that library, it's a header-only library that complements the OpenCL C language and allows you to sort of address past tensors and apply tiling in a fairly convenient way. So once we've generated OpenCL C code, we use LLVM-based compilers to translate to the VMP, to the PMA, to the MPC accelerators, whether they're VLIW, SIMD. So for SIMD, we of course leverage LLVM's vectorizer, which we're also maintaining for many years and helping to refactor. And we're trying to use as many of the target existing optimizations that are appropriate, and also introduce optimizations that are target specific for us, and of course generate code for our accelerators. And in that respect, we've also published this paper earlier this year, where if you take the standard pass pipeline of LLVM, it sort of not always does what you want. So if you want to compile for a CGRA or a VMP SIMD VLIW, then essentially you must compile, nested loops, right? You need to get rid of all the branches. And you can do that, and LLVM does that, but it does that fairly late in the pass pipeline, right? When you reach the target. What this talk suggests is when you're compiling for a target that needs to avoid branches, it's better to try and take them out of the game earlier in the pass pipeline. So that's some contribution to this part of the compiler toolchain.
A quick question on that. I guess given this pipeline, it wouldn't make much sense, but wouldn't this, so I actually read this paper, and wouldn't this be easier to do on the MLIR level? Again, this is probably not making sense in this pipeline because it seems you're going through OpenCL, so kind of you can't go the other way around. But yeah, I would be interested in knowing what you think about that.
That is an excellent question. Part of the answer is chronologically speaking. we support OpenCL as sort of a programming model and programming language for things that we want to code to run on these accelerators that do not come from AI frameworks. So this is a user-facing model, which doesn't go through MLIR, and it was actually built before MLIR was sort of available. So historically speaking, this was available, and we sort of reused it. Going forward, whether some of this technology could be actually imported into the MLR side of things, I think that's a very good question, and sort of it's an open question. There is a vectorizer here. There's a vectorizer there. Where's the best part to do it? Yes, we'll need to see.
I see.
So diving into one example of tiling. So suppose you have an image in main memory that you want to flip horizontally. By the way, which accelerator would best be used to flip an image in memory? Which would you use?
GPU.
A GPU.
Either what was the one that did super fast integer? Was that the VLIW SIMD one?
Yes.
Yeah.
Yes.
That's my guess.
Yes. So this is exactly right. I mean, you don't need a deep CGRA pipeline. There's not much compute going on. You just move bytes around, and it's very regular, right? So you don't need a multi-threaded sum. So this is the VLIW SIMD can take care of that. But the VLIW SIMD, as well as the CGRA, are accelerators that work with their own scratchpad memory. That's how they sort of do things fast, right? In parallel, they do it using their own software-managed cache or scratchpad memory. So there's a DMA engine that works in parallel to the compute engine. You need to sort of tile because you can't work on the entire image, right? So what do? You break it into parts, and you import it over to your scratchpad memory. You run the compute engine to flip it, and then you export it back, and you do it one tile after the other, right? And as you can see, it takes time, right? So you need to figure out how to tile, and then you need to figure out, well, maybe there are many ways, different ways to tile it. What's the best tile size? And how do we try to parallelize things, right? So you can overlap the import of the next tile with the compute of the current tile, right? With the export of the previous tile. So you can do a three-stage pipeline. But some in TTL, that tensor tiling library I talked about earlier, helps you to do that. There are, if you look at this tiling optimization, which is just one transformation we're sort of working with, there are different considerations and competing demands, right? You can take a convolution, and if it works with a very large image, you can tile the image. And if you process that image one tile after the other, you can keep the weights because they're invariant across the tiles of the given image, right? But then if you hit the next convolution, all these tiles that the first convolution produced are outside in main memory. So you actually spill them out, and now you need to fill them back in. Another option is if you have two convolutions, one feeding the other, then as soon as the first convolution computed one tile worth of data, go ahead and compute the next convolution. But that next convolution needs a different set of weights. So you sort of need to switch weights between different convolutions, and this is sort of a vertical tiling. And so which is better? What's the size of the weights? Do I want to bring them in after each layer? Do I want to get rid of, make sure I'm reusing the weights as much as possible? We talked about the fact that you can, if you remember back in that triangle, there's an option to do redundant work, right? So suppose if I'm doing convolution, then what results in having tiles that actually overlap, right? Because tiles need to also look at beyond their edges in order to, the output tile is smaller than the input tile. So you sort of have, if you bring in the different tiles, you can actually, if you want to optimize for parallelism, you can sort of say, okay, I'm going to import all the data I need, although maybe part of it was already brought earlier. So you either need to bring it again, redundant work, or I need to maintain it in my scratchpad. So you need to figure out how to handle overlaps. And again, that tiling library at least helps in some respect to deal with that. We can do double buffering, as we talked about earlier. When you compute something, import the next in parallel, because these DMA engines are work on parallel threads with the compute engine, and do that in parallel to exporting the previous, right? But if you do that, well, now you need to allocate more buffers, right? Essentially, you're double, and so you may want to actually reduce the size of the buffers when you do that. But there's also a trade-off, because the compute engine itself works best when there's sufficiently large tiles to work on, right? You need to fill the vector with or the CG array in order to maximize your utilization. So there are multiple competing demands. Problem is challenging, and this is just one of the things we're sort of working on. Another aspect I want to briefly emphasize, because I did want to sort of stress the fact that we have to make sure that what we're doing provides the correct result, right? Super critical in this mission critical domain. And one of our ways of doing that is, if we look at that MLIR component, which takes care of tiling, generating OpenCL code with all the tiling that is needed to run on sort of a scratchpad-based accelerator, we can also use this MLIR engine to generate plain C++ code, which is version. Still with me, right?
We lost you for a minute. I think you're back with us now.
Okay, I'm back with you. Great. So the same MLIR-based tool, in parallel to applying the tiling and generating optimized code for the accelerator, can also generate a C reference code for each of for the same sort of code that we're generating. And that C++ code doesn't have to worry about tiling, scratch pads, or anything. It's a general reference code. We can actually use a different compiler to compile it for an arbitrary CPU, right? And we can run this reference code that's sort of independent of this tool chain, which is sort of a reference, think of -0, right? We're not applying optimizations, we're doing it in parallel. And then we're going to compare the two and make sure they are last bit accurate, right? We want to make sure we keep the semantics. So that's a way of validating that the results are intact. And what if there is a mismatch? How do we support debugging, right? Errors happen, right? We're not perfect. The important thing is to sort of be able to reason about them. So there is also a way of taking this OpenCL version, tiled and optimized for the accelerator, and sort of circumvent the LLVM compilers and generate a C version for them. And from there, we can also, go through the independent compiler and execution environment. And but that's sort of a greater, finer granularity of kernels, which help us pinpoint and what's the term? Hunt the bug down. Okay, so let me stop here. If there are more questions, because I think we're sort of starting to run out of time. There's more information I can sort of try to cover, but this is the main message I really wanted to to leave you with.
Great, thanks a lot, Ayal. I mean, well, let's give Ayal an applause for now. We're gonna have one. All right, so I just want to remind people here, you can always grab the mic. You can go into the online chat. People on Zoom, you can also grab the mic, send messages to the Zoom chat, to me personally, whatever you want. I'm going to, I guess, start with a question on the last slide, which is that, in your experience, how much trouble have the already established compilers themselves have caused in your pipeline? So to put it simply, have you found bugs in LLVM?
I think we found bugs in LLVM. I think they're more related to how we ported LLVM to our targets than maybe core LLVM, or maybe we sort of exercised LLVM in ways that it wasn't before. Because again, this early if conversion work was exercising the tool chain, the LLVM pass manager, in ways it sort of wasn't so much tested before. And when doing that, yes, there are corner cases that one finds and and helps fix, right?
I see. Okay, we have a question from Zoom. Oh, wait, what happened to the chat? Oh, there we go. All right. How do you choose the best target for specific subprograms? Is it based on a cost model, or more like this chip is best for matmul? So I guess the second sounds like a simple set of heuristics.
Yes, it goes. I mean, when it goes back to the software hardware co-design, when we sort of sit with the CPU accelerator architects and design the capabilities. Sort of, we have a good understanding of which architecture is good for what. So yes, if you have a convolution, then by all means, there is an accelerator that excels at that. So that's sort of an easy. If there's something it cannot do, then yeah, by way of elimination, let's try the next powerful accelerator. If it's good at that, then we go there, and it goes down. Sort of that's a crude way of assigning accelerators to parts of the program, which could be good enough. On the other hand, you can think of sort of a critical path way of approach, which sort of says, I want to make sure the critical path is assigned the best accelerators to handle, and then things off the critical path or less critical, maybe it's not that important that they be assigned the best accelerator to run them, right? Because we sort of want to make sure that the best accelerators handle the critical path first and foremost, and are not starved by doing other things they can do, but which are less critical.
Yeah, we have another question from Russell.
Yeah, so I think this question kind of relates to the last one, which is, I saw on one of the slides, you mentioned one of the things you do at the MLIR level is a graph partitioning, where you have so I assume something that looks like an operator graph, and you kind of partition it into chunks that each individually go onto individual accelerators. Could you speak maybe a little bit to how you approach that partitioning problem?
So
Yeah,
in general, you yeah. Okay. Again, it boils back to the previous question about you want to see which layer works best on which accelerator, but then there's also layer fusion, which is highlighted here. So you actually want parts to be sufficiently large because you don't want to switch between accelerators. So there is sort of a coarsening argument to be had here.
Yeah.
So you may have a layer that, like this mirror image mirroring layer. Well, a VMP can do it, but the PMA can also. So is it that important to assign it to a VMP? Well, it depends, right? If the previous and the next layers are assigned to a PMA, then maybe it's better to keep everything within a PMA instead of going and communicating between accelerators instead of inside the same accelerator. Again, it's sort of a trade-off between parallelism and locality, if you like. And again, there are different accelerator types and multiple instances. So it's a balance, right? You need to sort of figure out how are we employing the amount of parallelism that we have, and also take care to optimize for locality where it exists and where it really pays off.
I see. And then when the compiler actually goes to, decide what partitions to place things in, is this mostly like the user is expected to kind of give a good partitioning, and then based on that user specification, the compiler will do best effort, or does the compiler try to automatically come up with the partitioning?
So there's of course a way to instruct which layer should go where, and this sort of goes back to is this auto tune or manual tuned? So yes, there's a lot of work to that is sort of still making sure manually that things are appropriately assigned, and analyzing the behavior and going back and fixing things. Yeah.
Thank you.
All right. So I just want to check and make sure we're not keeping you, right? If you need to go, that's fine. We have we have one question. Maybe I have two more, if that's fine with you. Okay, cool. So one question we have from the Zoom audience is, might have missed this. Is there pipelining across accelerators? For example, computing a flipped tile on accelerator 1 and performing convolution in accelerator 2.
If you think of the way sort of OpenCL works, then you can think of different n-deranged kernels running in some dependence graph one after the other. That's the coarse grain approach of leveraging an OpenCL model across multiple devices in this heterogeneous platform.
Yeah. Okay. Cool. I guess.
And again, it goes back to parallelism versus locality, which is better. It's a challenge to balance things.
Okay. I would like to finish our discussion, maybe others who have other questions, with maybe two more kind of generic questions that I think you may have good insights in. One I would like to ask is, you seem to have at least one long-term collaborator. If I pronounce the name correctly, it's Dorit Nussman. You've done pretty like seminal works together, and you've been working together, I think, more than 10 years. So if you could give us maybe your take on collaborations and what kind of makes for good long-term collaborators, especially you're talking to people that are like in a PhD program embedded in academia, and where sometimes it tends to be a little bit competitive.
That's a very good point. Yes, so Dorit worked with me back, and I think we go back from around year 2000. She worked with me at IBM. She developed the GCC vectorizer back when in our team at IBM. And she's working with me now in Mobileye and working with me at Intel. I can say that for me personally, finding the people that you best work with has been critical. Right? And it's, the way I see it, it's mostly chemistry, right? The people you sort of like and exchange ideas and collaborate with the best make the work much more enjoyable, much more productive. And there are other people that, but it's very hard for me to work with. So, and I don't really understand why, but it's sort of, there's so much effort you can spend in trying to collaborate with colleagues that you find hard to collaborate with. As if you find good colleagues, and this also goes to supervisors and teammates. If you find people you appreciate and they appreciate you, and you have a good collaboration with, you don't find yourself arguing. Well, arguing is good, but you sort of transmit on the same wavelengths. You don't need to explain too many times the same. The concepts are bounce your ideas against. That is, for me, has been most enjoyable. That's what I really cherish. And yeah, it's not always easy, and it doesn't work always, and I don't know why it works when it works and why it doesn't where it doesn't. But I do understand that it doesn't always work, and you should be thankful and grateful for cases where it does, and yeah.
Thanks for sharing that. Yeah, give her our best. She's been very inspiring. But I personally hope to see some content from her, like articles, talks, something like that. Yeah. I guess the other question is, obviously you've done a lot of academic research, of conferences. It's kind of a cliche question, but maybe you can tell us your take on it, on academia versus industry for a researcher. I guess specifically a compiler researcher, and whether your decision today would be different than when you chose, I don't know what was the last time you were thinking about that, but whether you think the factors have changed in 2024.
So I have, during my whole career, starting from master's degree, I've been sort of working in industry and studying and being involved in academia in parallel. And for me, working on something that's at the edge of research is something I really strive. I want to work on some things that first I want to understand if what I'm working on has already been solved. So read a lot, listen to talks, research, look for what people have already done, and try to bring it in to what it is you're doing, and try to come up with things and publish it. So I think this interaction with academia is super exciting for me for all my career. Right? That's what I think that's what's been most interesting for me. Being able to talk about what I do in meetups like this. So working with open source has been something I really emphasize in. Right? Being able to TTL this library, let's open source it, right? I can talk about it, I can share my experience, I can figure out if somebody else has done something similar, maybe better. We can collaborate for the better good Many problems we're solving internally in industry, wherever, are not really unique to Mobileye or to Intel. People have maybe invested in solving them. Maybe they see it differently. Maybe they being able to leverage the quality based of LLVM is sort of a very good example. There's a lot of research that has gone into the production quality of an LLVM based compiler. That is no parallel, right? That's something industry learned. Some vendors learn later than others, but all vendors learned eventually that it's foolish to think that you can sort of invent it all in-house and not pay attention to what's happening outside. And outside includes research and includes academia. And in compiler, it's sort of a very empirical domain where you actually need not only to come up with solutions, but also prove that they solve problems. So I think industry has a good chance of coming up with real problems. I want to drive the car automatically, right? I know what the problem looks like. I know what's challenging. I know what's really moving the needle and what's paying off, right, financially. Academia has a better chance of, investing long-term efforts in, coming up with, the infrastructure and innovative directions that can then help. So I really see the synergy in a lot of respects. And I think both directions are really striving for this interaction.
I see. Yeah, it makes sense. And if I may say that, I think it's very nice in LLVM where you see all these people. You talked about open source, and you have all these people from different companies come together, giving talks that don't look like advertisements or like selfish. Like this is what I care about. It's more of a collaborative effort, and definitely, I guess you've experienced that in vPlan, where you collaborated, I guess, with a lot of people who were involved in loop optimizations. Yeah. Interesting. Okay. So I guess, well, I don't want to skip a question, so maybe I'm sorry. I'm going to ask it. It just came here. It might be a dumb obvious question, but isn't it possible to automatically test the post-quantization compiled program by executing it against the reference one by using property testing in combination with some thresholds?
So we test it, right? It's not that we're not testing it, but we need to, and it's going to produce some different results, right? Now the question is whether so you run a floating point based program, right?
Mhm.
And you make some quantization changes to it. Now you run it and you get a different answer numerically.
Yeah.
Now it might be the case that numerical distinction is tolerable. It might be that it's not. Somebody needs to say whether that epsilon change is small enough, right?
Yeah.
And so we're very clear on who gets to decide what epsilon is, right? It's not me. Okay.
Right. So yeah. So I guess maybe you're saying that essentially, possibly the epsilon is like different for different programs, and figuring out even what the epsilon is like a manual effort where you have to go and check that. Yeah, this is kind of okay. This is not.
Exactly. Yeah.
Okay. All right. Great. I mean, thank you. You have a thanks from the person who asked that. And thank you very much for joining us today. I think this was really interesting. We hope to see more content from you. Talks at the LLVM meetup. This have always been great. And yeah, I would say let's give another round of applause to Ayal.
Thank you, guys. Excellent questions. Keep it up. I hope to have better answers, in the future.
Yeah, sure. Okay, great. Have a great rest of your day.
Thank you. You too.
Thank you.
Thank you.
Bye-bye.
Bye.